what is the Thevenin's theorem? Okay, so Thevenin's theorem is actually a fundamental concept in electrical circuit theory that simplifies a complex circuit into a simpler equivalent lah. Okay, simpler equivalent, which is we have a voltage source where we call it as a Thevenin voltage in series with a resistor, a Thevenin resistor lah, which is we call it as a RTH. Okay, so this theorem stated that any linear two-terminal networks, which is two-terminal network, which is a network with two connection points or terminals. So a network, you have a network where it connected with these two connection point or terminals lah. These terminals can be A or B ports lah. Okay, and then this linear circuit can be replaced by the equivalent circuit where we can have this Thevenin voltage here VTH with RTH here. So we can replace complex circuit of linear linear circuit terminals, and then we can replace it with this equivalent Thevenin circuit lah. Okay. All right. So when you have this equivalent circuit, this circuit is not affecting the operations of the rest of the circuit lah. Okay, so you don't have to worry from your complex circuit. Then when you want to turn it into these Thevenin theorems, so that's not going to be affecting anything on your operations of your circuit lah. Okay, and then after that, we have like a property of the linear circuit, right? So we know that previously I said that the two terminals network can be replaced by an equivalent circuit, which is consisting of a voltage source, which is Thevenin voltage, all right? Which is Thevenin voltage here, and in series with Thevenin voltage, which is, and then in series with this Thevenin resistance lah. Okay, so we have two things about this two terminal linear circuit, where we have a linearity itself, the linearity, two terms lah, we call it, we have a linearity, and as well we have two ports for this Thevenin lah. So the linearity here means that this theorem means that this Thevenin theorem apply only to a linear circuit. So what does that mean by a linear circuit? So linear circuit meaning that the relationship between the current and voltage is linear with each other. Like for, if you're using the Ohm's law, right, you know that your circuit is actually V equal to IR. So this one is proportional with each other lah. Okay, so that's, we call it as a linear lah. But we also have the non-linear components such as diode or transistor lah, which is not suitable for analysis using Thevenin theorems lah. Okay, and also we have two terminal networks lah. Okay, we have two terminal networks. These two terminal networks mean that you have the circuit with only two terminals. Often we refer that terminal with A and B ports lah, which is here lah. These two, we call it this one as a two terminal circuit lah. Okay, two terminal networks. So means that the goal for this Thevenin theorem is that we want to determine the equivalent Thevenin voltage and Thevenin resistance across these two terminals lah. So means that from these two terminals, we want to get the Thevenin voltage and as well of the resistance, Thevenin resistance lah. Okay. So for example, okay, so if you have this circuit, you want, the question asks you to get the Thevenin equivalent, right? So from this circuit, you know that you have this two-port network circuit, and then you need to transform this circuit into this Thevenin voltage and Thevenin resistance lah. So you need to calculate the value for the Thevenin voltage. Okay, from this circuit, actually, you know that Thevenin voltage is actually equal to open circuit voltage, or from this circuit you know that the open circuit voltage is actually referring to this VAB lah. Okay, so referring to this VAB, or for this one also seems like this V1 lah. Okay, and then after that you can calculate VAB from that lah, and then is actually from this circuit in order to calculate your RTH. Okay, RTH. So you can see that you have this independent circuit, right? So you can just turn off this independent circuit, and then you can calculate for your resistor. Okay, for example, if you redraw again this circuit, okay, just redraw here. If you want to calculate for the RTH, you can just turn off this circuit at this source. Okay, so now if you redraw again your circuit, you will have only this lah. Okay, which is this terminal where this is your 5, 20 and 4 ohm resistor, and then this is your terminal. So you can get this RTH by using the series and parallel resistor techniques lah. Okay, so your terminal is here, so means that you need to calculate your resistor from here lah. So from here you know that your RTH is equal to 5 is parallel with 20, right? 5 parallel with 20, and then you need to plus with 4, so you can get the value for RTH. Okay, is easy as that lah if you only have the independent source. But if you have the dependent source in your circuits, that's going to be any other case lah, different cases lah. All right, so we're going to look at that lah. Okay, how to calculate the Thevenin resistance if you have only dependent sources, only independent sources, or if you have the dependent source. So what we're going to do with that? All right. Okay, so this Thevenin theorems is replacing a two-terminal circuit, like I shown you in the previous slide. All right, so this two-terminal circuit, this one lah, we call it as this two-terminal circuit lah. So means that inside the two-terminal circuit, this is your circuit lah, and then connected with this terminal. All right, and then we want to convert it into this Thevenin equivalent circuit lah. All right, where we have VTH and RTH here. Okay. So, how can we calculate the Thevenin voltage? So, to calculate this Thevenin voltage, you need to look back again your techniques, like you have learned about the circuit analysis, right? Where you have node, mesh, superposition, source transformation, parallel series resistor, Ohm's law. So you can use all that techniques in order to calculate for your Thevenin voltage lah. And then you know that the fundamental for this Thevenin voltage is that your Thevenin voltage is actually equal to this VOC. Okay, so if you have the two terminal circuit, so you need to calculate your VTH is here lah. Okay, which is equal to this open circuit voltage at this port A and B lah. Okay. Like for these examples, like I said before, so means that this is your VTH. Okay, here is your VTH, which is equal to this VOC lah. Okay, and then we have, okay, we have this Thevenin resistance. So we have a few methods in order to calculate for this Thevenin. So Thevenin resistance is actually equal to R in here lah. Input resistance at the dead circuit of A and B port here. So if you have all the independent source, you can just using this method one lah. Okay, so means that if your network has no dependent source, means that you have only all the independent source. Okay, you mean that you have all the independent source. So you might use this method one lah for your RTH in order to calculate RTH. So how you can do that, which is by turning off all your independent source, like for this example. All right. So if the question asks you to calculate the RTH, what you can do, because you know that here you only have the independent source, right? you only have the independent source here. So you know that two independent source, which is a 5 volts and 2 milliampere current source lah. So you can just turn off this one, and then you know that by turning off this voltage source, you will have a short circuit, and then when you turning off this current source, you're gonna have the open circuit lah. So when you turn off these two, so you might redraw again your circuit, which is this circuit lah. And so now you can calculate for your RTH, all right? So this is your terminal, so you might start calculating from this side lah, okay? So like for this one, obviously your RTH is actually 5 parallel with 20, okay? 5K parallel with 20K, and then you can plus it with 5K, right? Here, 5 kilo ohm, and then it's parallel again with this 6K, and then you can get the value for your RTH. You need to calculate lah. So then you get your value for your RTH for this example when you have all independent source lah. Okay, so we have another two methods where that method we use it if you have dependent sources in your circuit lah. Okay, so for example, if you have these dependent sources, okay, you might use this method too, where you need to add this test voltage, or we call it as a test current and test voltage lah, where this value V naught is equal to 1 or I naught is equal to 1, where if you put the test voltage here, in order to calculate the RTH, if your V naught here 1, so you need to get the value for I naught lah from the circuit. Okay, and then you can calculate for RTH. But if you put the current source, source as a test, so you need to put I naught is equal to 1, and then you need to calculate the value for V naught lah, because RTH is equal to V naught over I naught, where V naught over your I naught is 1 lah. So then you can get the value for your RTH. Okay, so using this method, you need to also turn off your independent source lah, and then get the value which source that you use, whether you use your voltage source as your test source, or you can use the current source lah. So it's either one lah. Okay, so like for example, for this method, what you can do is that you still need to turn off the independent source. Like if you have this circuit, all right, you know that you have this dependent, this is the dependent source lah. You have the dependent source, you only have one dependent source. Okay, so you know that when you apply the test voltage or current here, like for this one, it's using the test voltage here, where you know that this V naught is actually equal to 1, and then you need to calculate the value for I naught, because you know that your RTH is equal to V naught over I naught, where your V naught here is 1, and then you need to calculate the value for I naught here. And then also, if you redraw again this circuit, you need to turn off this independent source lah. Okay, so this is method 2. You can use the method 2. Using this method 2 is up to you lah, whether you want put here the voltage source or current source, is up to you lah, which one is more easier or more convenient for you lah to do the calculations. Okay, so we have another method where we have method 3. So if you have a network with the dependent sources, you need to connect the terminals A and B by short circuit lah. Mean that you can put terminal A and B by short circuit, and then you need to find the short circuit current, which is we put it as a ISC here. ISC by utilizing circuit analysis methods such as nodal and mesh analysis lah. You might use the nodal or mesh analysis or any other methods lah. And then you can find that your Thevenin voltage is actually equal to VOC over ISC. So then you can get the value for RTH. So VOC here obviously equal to VTH lah. And then your IC here, you need to calculate your IC here lah. So then you can get the value for RTH. For example, you have this dependent, right? Same like a previous circuit as a method 2 lah, okay? If you just put a wire here to make here as ISC, okay, this is going to be your ISC, you can just leave this independent source. Okay, like method 2, if you add the test voltage or test current here, you need to turn off this, right? But for the method 3, you can just leave this voltage source lah, and then you can calculate to get the value for ISC here. Okay, so that's about the ISC lah. So you can use this equation lah to get the RTH. Okay, so means that if we summarize lah, in order to calculate your for your RTH, we have 3 methods lah. Okay, so we have 3 methods. For a first method where we have all the, this analysis is based on the source that you have, all right? Okay, for the first method, if you have all the independent source, so means that you can just turn off this independent source and calculate for your RTH. Okay, so for this second and third method where you have dependent source on your circuit, so then by using a method 2, you can use the test voltage or current, where you can put this as your V naught or I naught, where the US is going to be equal to 1 lah. And then also you need to turn off the independent source if you have in the circuit lah. Okay, and then we have another one, which is the method 3, where you can calculate for ISC by using the circuit. The circuit, you don't have to turn off the independent also on lah. Just add this ISC at terminal A and B. Add ISC at terminal A, B lah, and then you can calculate for your ISC, and then you can use, in order to get RTH, you can use this equation lah, where you know that VOC is equal to VTH, and then you can divide it by ISC, the one that you have calculated, and then you can get the value for Thevenin resistance lah. Okay, so this is the 3 method that you might use in your question in order to find the answer for your RTH lah. Alright, so okay, and just for a note lah here. So when you calculate for your Thevenin resistance, you might find that you will have the negative Thevenin voltage lah. So this Thevenin resistance might be a negative, because it means that it indicated that your circuit has ability to provide or supplying a power lah. Okay, for a circuit. Okay, so now I think that, also we have this, okay, from the Thevenin equivalent, you also can calculate to get the value for the load current and also the load voltage lah. Okay, so you have this linear circuit, and then you have transformed your circuit into this Thevenin equivalent circuit lah. So we call it this one as your Thevenin equivalent circuit lah. Okay, equivalent circuit. So from this one, you already have calculate for the Thevenin voltage and Thevenin resistance. And you note that from this one, from this circuit, you can get the value for IL using these equations lah, where your IL is actually equal to VTH over RTH plus with this RL lah. Okay, so because you know that this is your IL, right? So you can just calculate VTH over, because I equal to V over R, right? So V over your total for RTH and RL lah. So then you can get the value for your IL. And then you can use the voltage divider in order to calculate for this VL lah. So I think that you still remember, right? The voltage divider. So means that here is actually your VL lah. So VL, let's say here is your VL. So you can calculate to get the VL, which is using this equation where you have RL over RTH plus with RL, then times with your VTH, and then you can get the value for your load voltage lah. Okay, so you might just remember these equations lah. If you have this, if you have finished calculating for the VTH and RTH, means that you can get this Thevenin equivalent circuit, and then from this circuit you can get these two value where you can calculate for the current load and voltage load lah. Okay. Alright. Okay. So we can have this example. The first example. Okay. From this first example, you notice that you only have independent source in this circuit. So means that what method can you use? If you have all the independent source, so you can use the method in order to calculate RTH, you can use method 1, right? So what is the method 1? Method 1 is just turn off all these sources and then redraw again your circuit, then you can calculate for your RTH. Means that from this, you redraw again your circuit, so you know that you will get this circuit lah. Okay. So this is your terminal A and B. So you will have this 4, 12, and 1. So in order to get your RTH is equal to, so 4 is parallel with 12, right? 4 parallel with 12. And then plus with this 1. Plus with 1. And then you can get the value for your RTH lah. Okay, so it's easy as that lah. If you don't have any dependent source in your circuit. Okay, so you can just do that lah. Alright, so if you calculate, you can get your RTH is equal to 4. Okay, by using this formula as I shown you lah. Okay, and then in order to calculate VTH, so where is your VTH? So you have this pot, right? A and B, so you know that your VTH is here lah. Okay, because you have this as open circuit, because VTH is also equal to VOC, right? So here is open circuit, so means that there is no connection for this 1 ohm resistor lah. So you can just ignore this 1 ohm resistor. So you might have only this circuit lah, okay? Because this is not nothing to do with this one lah. Alright, so for VTH, you can use the node voltage analysis lah, or if you comfortable or you know to calculate with other method, so you can just use any other method lah. But for this example, I'm using the node voltage analysis lah. Okay. Okay, if you remember, node voltage analysis is actually about the summation of positive current equal with summation of the negative current, right? So this is the node voltage. Okay, so from these current directions, you know that this is the node for VTH. So this is leaving the node, means that this is positive. This is entering the node, which is positive. And this is leaving the node where you have the negative. So means that you have two negative current here with one positive current lah. Okay, so if you put this one into your equation, so you know that for this negative current, you have VTH minus with 32 over 4. And for this current, you will have VTH over 12. And for this one, you will have 2 ampere lah. And then you can put it into this equation lah, okay? Where this is the, for this pipe, this one is actually your summation of your negative current, and this one is your positive current lah. Just rearrange that. And then by solving this equation, you need to simplify first. You might simplify that by multiply this equation with 12. And then when you calculate, you can get your VTH is equal to 30 volts. Okay, and then after that, you have your RTH and then you get your VTH. So now you can draw your Thevenin equivalent circuit lah. Okay, Thevenin equivalent circuit. So your Thevenin equivalent circuit is you have your voltage here, and then you have your RTH here at terminal A and B. So this is your VTH and then this is your RTH. Okay, if I ask you to draw the Thevenin equivalent circuit, so this is your Thevenin equivalent circuit lah. Okay, so we just put the VTH here, which is 30 volts, and then your RTH here is 4 ohm lah. Okay, so this is your Thevenin equivalent circuit lah. Okay. Alright, so this is your Thevenin equivalent circuit lah. Alright. But if the question also asks you to calculate this IL, so you can just use the equation lah, the previous equation that I have shown you, right? So you can use that lah. Okay. Okay, so okay, we have this exercise. So obviously lah, the question asks you to find the Thevenin equivalent. So this Thevenin equivalent means that you need to find for VTH and also for the RTH lah. So you need to find these two and then just draw again your equivalent Thevenin lah. Okay, so you have this circuit. This is actually the two terminal circuit lah. Okay, so this is two terminal circuit where we have the terminal is A and B. Okay. So now I think it's easy if you can calculate for RTH first. Okay, because in order to calculate your RTH, what you can do is that, just put it in this lah. Okay, first we can calculate your RTH by turning off this current source because you only have this independent source lah. So independent source, you can use the method 1. Okay, method 1. And then you can just turn off this. Then you can redraw again your circuit, right? So you will have this circuit lah, which is at terminal A and B. You will have this 3.2K, 20.8K, and then you have 56K. And then you can calculate your RTH is just start from this side lah, okay, because your terminal is here. So means that you will have parallel resistor, which is 3.2K plus with 28K. And then it's going to be parallel with 56K, which is this is going to be equal to 16.8 kilo ohm lah. So means that your RTH is equal to 16.8 kilo ohm. Okay. And then now you want to calculate for your VTH. You know that your VTH, okay, is equal to VOC, voltage open circuit here where it was here lah. So this is VTH, which is equal also with your VOC lah from this circuit. Okay, so you know that here is your VTH. Okay, so your VTH is from this current here lah. Okay, so now, so means that your VTH is actually equal to this R, this 56 KR times with this I here lah. You might put this I here, so then you can find the value for VTH. So okay, from this circuit, you know that you can use the current divider. Okay, it's easy, like you can use the current divider by just sum these two, total up these two resistor where you can have this circuit lah. Okay, or you can have this circuit where when you total up this part, 56 plus with 3.2, you know that when you add that 56K plus with 56K plus with 3.2K, you know that the value will be 59.2K lah. So here gonna be 59.2K, and then here it will be 20.8K lah. Okay, so now you want to find the I here in order to get this VTH here. Okay, so you need to get this I, let's say this is I1 and this is I2, right? So you have this 1 milliampere lah. Okay, by using the current divider, okay, in order to calculate this I1 equal to 20.8K over 59.2K plus with 20.8K times with 1 milli lah, okay, 1 milliampere. So now you have 20.8K over 80K. When you do the summation for these two resistors, you get 80K, and then you can times it with 1 milli, and then you know that your I1 here is actually equal to 0.26 milliampere. Okay, so now you want to get this VTH, right? VTH, so you just use this formula lah. Okay, VTH is actually equal to this I1 0.26 milli times with 56K lah. 56K, so that you know that your VTH is going to be 14.56 volts. All right, so you have already calculated for RTH and also VTH. So now you can redraw your equivalent circuit where you will have, this is going to be your VTH and this is going to be your RTH. Then you have terminal A and B lah. So your VTH is 14.56 volts, and for RTH you have 16.8 kilo ohm. Okay, so you've done finding this equivalent Thevenin lah. Okay, so this question asks you to calculate the Thevenin equivalent voltage, where this is VTH, and as well as the Thevenin equivalent resistance lah, which is RTH. So you need to calculate these two, and then okay. So first, analyze how to calculate the RTH first lah. Okay. So if you look at this circuit, okay, you know that you have a few methods, right? Which is method 1, method 2, and method 3 in order to calculate your RTH. Okay, so method 1 is all for the, if you have all the independent sources, you can just turn off lah. So it's like for this circuit, obviously you have only independent circuit in this circuit lah. So and you have only independent source in this circuit, so means that you can just turn off this, and then you can calculate for your RTH. Okay, so if we go here, in order to calculate your RTH, you can use the method 1 lah, method 1, where you can just turn off this. Okay, so means that if you redraw again the circuit, you can find that by turning off this voltage source, you will have the short circuit, and then you have this resistor, and then by turning off this, you will have open circuit lah, and then you will have this as you will have this lah, in order to calculate RTH for your circuit lah. So this gonna be 15K, and then this gonna be 30K, and then this one gonna be 5K, and then this one gonna be 10K lah. All right, so from here you might calculate from this side first lah. Okay, so obviously here 15K is parallel with 30K. Okay, and then when you have this value, you will have the series with 5K, and order it's again gonna be parallel with 10K. Okay, so then if you calculate this value, you find that your your VTH is actually equal to 6 kilo ohm. Okay. So it's going to be 6 kilo ohm lah for your RTH. And now I just put a border here, how to calculate for your VTH. So in order to calculate for VTH, so VTH is actually equal to your V open circuit here lah. So you know that this is the VOC, so this is your VTH, which is equal to this V2 as well. All right. So you can just directly put the VTH or V2 lah in your node here. So obviously here we can use the node voltage analysis lah. Okay. So here is your node, here is node 1 and here is your node 2 lah. So you know that using the node voltage analysis, you just need to sum the positive current with negative currents lah. So you might just put your directions of current lah. So let's say I just put it here like this and just follow this current, which is this way and then this way lah. Okay, so means that at node 1 we have these directions, for these directions, and also this one lah. We have four branch current lah. Means that we have V1 for this part. We have V1. We have V1 minus with 6 over 15K for this negative current. And this obviously you have 2 milliampere lah. And for this part here, you will have V1 over 30K. And then for this part here, for these directions of current, you will have V1 minus with, let's say we put VTH over 5K lah. So you will have four branch current for this node V1 lah. And then you just put it into where is the positive current and negative currents lah. For this one, you have this negative, this one is positive, this one is negative, and this one obviously the negative lah. So you can just add up that. Just for positive current, you have 2 milli equal to V1 minus 6 over 50K plus with V1 over 30K plus with V1 minus VTH over 5K. Okay, so this is your equation 1. And then your equation 2, which is here, you have this node V2. So let's say your current directions is entering and equal with the leaving current lah. So means that you will have these directions of current where you have V1 minus with VTH over 5K equal with this VTH over 10 lah. VTH over 10K. Okay, this is your second equation. So you need to solve for equation 1 and 2, and then you will get the value for your, I want you to try and then calculate by yourself lah. Okay, first always you need to simplify this equation, these two equations. And then you can use elimination method, you can use even substitution method. All right, so I think that for 2 equation you can use that both method lah in order to calculate for your V1 on or your VTH lah. Okay, so when you solve for these 2 equation, you can get the value for your V1 is equal to 14.4 volts, and for your VTH you will get 9.6 volt lah. Okay, so the important thing that you want to find from this equation is this VTH lah. So now you already get the value for your VTH, which is equal to 9.6 volt. So now you can just draw your Thevenin equivalent circuit lah. So this here is your Thevenin equivalent circuit. Okay, so where you have this voltage source, and then you have this terminal A and B, and then you have here is your RTH, then you have here is your VTH, and then just put the value where your VTH is 9.6 volts and then your RTH is 6 kilo ohm. All right, so you will have your Thevenin equivalent circuit lah. Okay, so I think that we move on with this example lah, another example. Okay, so this example, obviously you have this dependent source lah. You have this dependent source. So for your RTH, you might use the method 2 or method 3 lah, as previously shown to you. Okay. Okay, so method 2 is you apply to put the test voltage, or you can put the test current lah, where V naught or I naught equal to 1 lah. Or you can use this method 3, where you can put the ISC at the open circuit, and then you can calculate for your RTH, which is equal to VTH over ISC. Okay, and then for this method as well, you need to turn off your independent source lah, and then put the test voltage or test current on your circuit lah. So it's up to you which method that you want to use lah. But for this example, I'm showing you that we are using this method 2 lah, in order to calculate for the RTH, where we just turn off this and then we replace here with the test voltage. All right. Okay, let's see how we find our RTH in this circuit lah. Alright, you notice that from this circuit, when we turn off this, okay, we turn off the 5 ampere source, and then we put here at the pot here, we put the test voltage, which is equal to 1, and then we need to find the value for I naught, because we know that RTH is equal to V naught over I naught, where your V naught here 1, and then you need to find the value for I naught here lah. So then you can get the value for your RTH. Okay, so by looking at this circuit, it's obviously that this one using the mesh analysis lah. Okay, we are using the mesh analysis. So using the mesh analysis, we have 3 mesh here lah, obviously. From here we have 3 mesh. Okay, let's say from this loop 1 here, which is I1 here, you know that we're going to have this negative 2 Vx plus with 2I minus with 2I2 lah. Okay, and then equal to 0, and then when you simplify this equation, you will get this lah, which is Vx equal to I1 minus I2. And what is the value for your Vx? Okay, so you know that your Vx is actually equal to 4 times with I2, which is, you know that V equal to IR, right? So this is your Vx, and then your I here obviously is I2, and then your R here is actually 4 lah, which is 4. So Vx is equal to I2 times with 4 lah. Okay, because the directions of current is this one, so you just put the negative here lah. Okay, the negative Vx. Okay. And then this I2, and then this equal to I1 minus with I2, because you know that Vx here, if you look at here, your Vx here is equal to I1 minus I2. So means that your negative 4 I2 is actually equal to I1 minus with I2. Then when you simplify, you get this I1 equal to negative 3 I2 lah. So means like negative 4 I2 equal to I1 minus with I2. Then you can just bring this one here, where you can have negative 3 I2 equal to I1. So that's why you will have this I1 equal to negative 3 I2 lah. Okay. So you have that for your loop 1 lah. And then we're gonna have look at the loops 2 and loops 3 here lah, which is I1, I2 and I3. So you will have at loops 2, you will have 4 I2 here, 4 I2 plus with 2 I2 minus with 2 I1, and then plus with 6 I2 minus with 6 I3, or you can just straight away do like just sum of this 4 plus with 2, 6 plus with 6, which is 12 I2 minus with 2 I1 minus with 6 I3 equal to 0 lah. Okay. So this is gonna be your mesh at I2 lah. This is at loop 2, and then for 3 here, okay, for these 3 you will have just add this, okay, where you have v naught equal to 1 here, so you will have 8i3 minus with 6i2 plus with 1 equal to 0. So this is in your mesh tree, and then you can solve for these two equations, and then you can have the I3 is equal to negative 1 over 6 ampere lah. Okay, and then you know that I naught here, so now you can get the value for your I3 lah. Actually, you can just substitute this lah, okay, which is I1 is equal to negative 3I2 in this equation. So then when you solve that, so you know that your I1 is actually equal to negative 3I2. So you can just substitute this I1 in one of this equation, and you can solve for this equation lah in order to get I3 lah, okay. Then when you solve for that, you get that I3 is equal to negative 1 over 6. And then you know that I naught here, we want to find this I naught because we know that your RTH is equal to V naught over I naught. All right, we want to get this value. Where is this value? So I naught is obviously is this mesh lah, which is equal to this I3. So because of the direction is opposite, right? So this one is here and this directions of I3 is here. So you need to put the negative I3 lah for the I naught. So means that your I naught is equal to negative I3. So your I3 is actually equal to negative 1.6 with the negative, so that you will have I naught is 1.6 ampere lah. And then your RTH is, you know that this is your V naught, which is equal to 1. And then your I naught is 1 over 6. Then when you solve for this, you can get your RTH is equal to 6 ohm. And then you can have your then you can, after that, you can calculate for your RTH lah, because you already have the RTH, which is equal to 6 ohm. Okay. And then now we can calculate for VTH lah, the Thevenin voltage, where for this one as well, it uses the mesh analysis lah. Okay, so from this, you know that this is your VOC, which is equal to your VTH. So this is your VTH here lah, which is obviously here your VTH is, so this is not, this resistor is not functioning lah, because this is the open circuit, so there's no connection for this 2 ohms. So your VTH is here, where if you're using this mesh analysis like this circuit, you know that this VTH here is actually equal to VTH here is equal to 6 ohm times with this I2. So means that you need to find the value for this I2 in order to find your VTH. Okay, so by using this circuit, you know that your I1 is obviously this 5 lah. Your I1 is equal to 5 ohm. So this is the loop for I1. So it was actually equal to 5. And then in loop 2 here, you know that when you simplify, you can get 4 plus with 2 plus with 6, you will have 12I2 minus with 4 times with I1, which is 4 times with 5, okay, and then minus with 2 I3 lah, equal to 0, okay. So you will have this, where when you simplify, you can get 12I2 here, 12I2 minus with 2I3 equal to, when you bring this 20 here, so you can get this equation lah, okay, from the loop 2. And then obviously from this mesh I3, you will have 2I3 minus with 2I2 minus with 2Vx equal to 0. Okay. And then you know that okay, so you will have that, and then you know that your Vx here, okay, your Vx here is actually equal to 20, right? Your Vx here equal to 20. Why is it 20? Because here is 4 times with 5, right? Here, your Vx here equal to Vx here equal to I1 my times with 4, which is 5 times with 4, then you get here is 20 lah. So when you times it here, you can get 40. So that's why you will have this equation lah as your equation for your loop 3 lah. Okay. And then sorry guys, for this is you cannot just directly times this with for I, because this one is I1, okay, this one let's say IX, and this one is obviously your I2 here lah. Okay, so this is I2. So in order to get IX here is actually equal to Ix here is actually equal to I1 minus with I2, which is, betul tak? I1 minus with I2, which is Ix equal to 5 minus with I2 lah. So this is your Ix. Okay, so means that for your Vx here, Vx is Ix times with 4. So you need to substitute this Ix by 5 minus with I2 times with 4. So then you need to rearrange again the equation. Just put Vx, just substitute Vx with 5 minus I2 times with 4. And then when you do the rearrangement, so you can get these equations lah, all right? Okay, so then when you solve for that, actually you can get, so you can solve for these two equations lah. Okay, equation from loop 2 and loop 3. So now you can get I2 is equal to 60 over 80. Okay, so now you already get your value for I2. So you know that your VTH is 6 times with I2. So 6 times with your 60 over 80. So then you can get your VTH is equal to 20 volts lah. And then you know that your equivalent circuit is, this is VTH, and so this is your RTH lah. Okay. Okay, so for this exercise, obviously lah, Thevenin resistance where you need to find the VTH and RTH lah. Okay, so this circuit have the dependent source, right? You have the dependent source. You have the dependent source, which is the current source, or dependent current source, where you have it 1.5 Ix. And then you can, so means that you can choose for your RTH which method you want to use, where you can use method 2 or method 3 lah. Okay, it's up to you. And then in order to calculate VTH, is obviously this is your VTH lah. All right, so this is your VTH. So you need to get the value for I here, and then you can calculate for VTH, or you can directly use any other method lah, whether you can use the mesh or node analysis in order to calculate for your VTH. Okay, so for this question, you can calculate your VTH by using mesh analysis. Why we are using the mesh analysis, not the node analysis? Because I think that because we have this current source here, right? So we have a dependent current source here. So if you remember that we can create a super mesh here, right? So it will make our calculations is more simplified lah, because we have this super mesh here. So means like you have this mesh I1 here and like let's say I2 here. So you need to have two equation from this super mesh, and then another one is node 0 here lah. Okay, where you have these connections lah. Okay, so from here you can calculate for your VTH, where your VTH is here. So you know that your VTH here is equal to 4 times with I2 lah, 4 times with I2. So then you can get the value for your VTH. So now let's come up with the equations lah. Okay, so you know that your Ix here is equal to I2, obviously lah. Ix here is equal to I2, okay, because this is the same directions with this mesh I2 lah. Okay, so now let's come up with the equation at node 0 here. Okay, for your node 0, just draw again lah. This is your node 0. Okay, so this is your 1.5 Ix, and then this is your I2, and then this is your I1. Okay, so you know that from this node, you know that node 0 will be I2 is equal to this is I1, sorry, I2 equal to I1 plus with 1.5 Ix, and then you know that your Ix here is actually equal to I2. You can just substitute I1 plus with 1.5 I2 equal to I2. So you know that your I2 will be 1.5. When you bring it here, it will gonna be minus, right? How much is it? It's gonna be 0.5, right? Negative 0.5 I2 equal with I1, is it? Okay, so then you can have your I2 is equal to I1 minus I1 over 0.5, where you can find that 1 over 0.5, you can have 2, negative 2 I1 lah. So that's why you will have this equation lah as your equation 1. Okay, and then we need to also find the equation for a super mesh lah. Okay, so for super mesh from, okay, let's say we have this lah from here. What we have is we will have negative 6. Okay, negative 6 plus with 5 I1 plus with 3 I2 plus with 4 I2 equal to 0 lah. So when you simplify, you're gonna have negative 6 plus with 5 I1 plus with combine this value. So you will have 7 I2 equal to 0. Okay, so that's why you will have this as your equation 2 lah. And then you need to solve for 1 and 2, and then you can get I2 is equal to 4 over 3a. And then you already know that your VTH is actually equal to 4I2, right? So you just need to substitute I2 with this 4 over 3, and then when you calculate for your VTH, you know that your VTH is equal to 5.33 volts lah, all right? So now you already find the value for your VTH, okay? And now let's calculate for RTH lah. Okay, as I said before, you might use method 2 or method 3 lah for your RTH. But for this solution, actually we are using the method 2 lah, where we put this test voltage source here, where this is V node, which is equal to 1, and then we need to find this I lah, which is also I node lah. Okay, you need to find this I. Okay, so you can apply a node voltage method lah at this V node, and then you can find this value lah. Okay, so obviously from this V node here, what you have is at node V node here. Okay, just follow the current directions, right? You will have here V node over 5, and this one is obviously 1.5 Ix, and this one's going to be V node minus 1 over 3 lah, because this V node is already equal to 1 lah. Okay, and then just put it into the summation of positive current and the summation of the negative current lah. So this is going to be negative, negative, and this is positive. So this is the summation of the negative current equal to the summation of your positive current. Okay, you can just put it here and then you can just simplify lah. Okay, so you know that your Ix here, your Ix is here, right? So you know that your Ix here is actually equal to V naught minus 1 over 3. Okay, so you already know that your Ix is actually this one lah. V naught minus 1 over 3. This is your Ix. So you can just substitute your Ix here. Then you can calculate for your V naught. Then when you simplify, you can get your V naught is actually equal to negative 5 volts. Okay. And then at node 1 here, okay, you already have the value for V node is negative 5 volts. And then now at node 1 here, what you have is, this is the current directions for this node where you have the negative, negative, and the positive currents lah. Where you have this node, you already have the value for V node, right? So you will just can just calculate the value lah. So this V node is actually equal to negative 5. So negative 5 minus with 1 over 3 for these current directions, plus with 1 over 4. So this is the positive current, right? We have 2 positive current and 1 negative current lah. So negative 5 minus with 1 over 3 plus with 1 here, obviously, okay, this one. And then plus with I naught here lah. This current directions here is I naught, plus with I naught, and then which is this one equal to 1 over 4. So then when you calculate, you can get your I naught is equal to 2.25. And then you know that you can find your RTH. Okay, RTH is equal to V naught over I naught, where your V naught is 1 and your I naught is 2.25. Then when you calculate, so you can get the value is 444.4 milliohm lah for your RTH. Okay. Okay, guys. So this is your RTH. So now you already calculate for your VTH and then you calculate for your RTH, and you know that you can draw the equivalent circuit lah. Okay, draw equivalent circuit for your VTH, and this is your RTH lah. This is A and B. Just put the value lah. So then you're done with the Thevenin equivalent circuit for this circuit lah. Okay. Also, I also put another example. I think this one you might try it by your own lah, because I already put the solution here as well. Okay, you might try how to solve for this one. Okay. Right, because I want to go with the Norton theorems. Also, I've put this exercise as well. I put this method 2 and method 3 because we know that you have this dependent source, right? So whether you can use the method 2, so you will have the same answer lah. Also, if you're using the method 3, you will have the same answer with method 2. So if you're using the method 2, you need to turn off this independent source and then put the test voltage here, turn off the independent source, and then put the test voltage or current lah. Okay, And then for using method 3, you can just put the ISC here. Okay, you just can put the ISC here and then find the value, and then you know that your RTH is equal to VTH over ISC. Okay, so you can use this value lah. So means that if you're using the method 2, you need to turn off this and then put the test voltage or current here. And then if you're using this method 3, just put the ISC here. Okay, just put the ISC here, then you can calculate for ISC, then just divide it by VTH divide by ISC, then you can get your RTH lah. Okay, so you might try using this method 2 or method 3 lah, then you can get your answer. Okay. Okay, so Norton theorem is actually same like Thevenin equivalent lah. Okay, a Thevenin theorem, because Norton theorem is actually, okay, so use Thevenin, you need to calculate to get the voltage VTH and RTH, right? But for the Norton, you need to get the current source, all right? The current source, it will be parallel lah. Okay, this is terminal A and B lah. So means that for Norton theorem, you need to calculate for the Norton current, and then this is also the Norton Thevenin, which is this Norton, not Norton Thevenin, but Norton resistance, where the Norton resistance is equal to RTH. It's also the same value with the RTH, means that from the Thevenin equivalent circuit, you can turn your circuit to this Norton theorem lah, where you know that you can find your IN, which is equal to VTH over RTH from this circuit. So you can just turn from this, or you can turn from Norton to Thevenin. Okay, this is like source transformation lah for this theorem and Norton lah, which is you can have this Norton theorem current, which is equal to VTH over RTH. So mean that for Norton theorem, you need to find the Norton current and also the Norton resistance, where you know that Norton resistance is equal to the RTH resistance lah. Okay, and then for Thevenin, where we just learned just now, Thevenin is we need to find the Thevenin voltage, and then we need to find this Thevenin resistance lah, where this is the circuit, and then for the Norton, this is the equivalent Norton circuit lah. Okay, so it's just vice versa, the same techniques that you might use from the Thevenin theorem lah for the Norton theorem. Okay, so that's why here we said that similar to Thevenin theorems, Norton theorem seems okay linear two-terminal, where you have the linear two-terminal circuit A and B, which is at port A and B. This is two-terminal circuit lah. Okay, inside here can be replaced by equivalent circuit consisting of current, Norton current, and parallel with Norton resistance. Okay, at port A and B lah, which is IN is actually a short circuit current through here lah. So IN is equal to ISC, which is the short circuit current here through terminals A and B, and then RN is actually equal to input or equivalent resistance at terminal here lah. When the independent sources are turned off. So means that this is the case when you have all the independent sources in your circuit. So you can just turn off all the independent sources in order to find the value for equivalent resistance lah. Okay. Alright, so Norton equivalent circuit consists of an independent current source. So this is independent current source, which is parallel with this Norton resistance. Then can be derived from the Thevenin equivalent circuit simply by making a source transformation, as I said before lah. It's just vice versa from the Thevenin into the Norton theorems lah. Okay. So Norton current is IN, which is a short circuit current at terminal of interest, which is here lah. This is ISC, which is equal to IN lah. Okay. Norton resistance, which is RN, is equal to the Thevenin resistance RTH. So RN equal with RTH lah. Okay. So means that for Rn here, you can also use the same method like you used to calculate the RTH, where we have the tree method, right? So you can use any other method lah. You can choose any other method that you like in order to calculate for RN, because it seems like for the RTH lah. Okay. So right, okay, we have this example. Find the Norton equivalent circuit for below circuit at terminal A and B. Okay, so obviously from this circuit, we can calculate RTH by turning off these two sources lah. Okay, because there is no dependent source in this circuit. So directly we can just turn off this, and then we can just draw again the circuit where we will have this circuit lah. Okay, and then we can calculate for R. Okay, so here for R, TH is equal to 5 is parallel with 20, and then plus with 4. So this one gonna be equal to 8 lah. When you calculate, you can get 8 ohm lah. And then, okay, remember for in order to get IN, the way that you can calculate is that VTH over RTH, or you can just put calculate direct here ISC, because you know that ISC is equal to IN lah. You can choose any method lah in order to calculate directly ISC, which is equal to IN, or you can just use this formula lah. But I think that for me, I like to calculate for VTH first, and then because I already have the RTH, and then I can just calculate for the IN lah. Okay, then if I want to calculate for the VTH, so you know that here is the VTH, right? So here is actually the node for the VTH lah. So just draw the current directions here. So all is leaving the nodes, all right? So means that all you have the total of negative current equal to 0 lah, because there is no positive current here, okay? So the equation going to be for this part is going to be VTH minus with 25 over 5, okay? VTH minus with 25 over 5 plus with this one, VTH over 20, and then for this one, because it was opposite the directions of this one, we just put the negative lah, negative 3 equal to 0. So now you can get the value for VTH lah. So when you do the calculation, please to make sure that you simplify this circuit first by times it with 20, so that here you can get I think that this one going to be 1, and then here's going to 4. And you're going to have 4 VTH minus with 100 plus with VTH minus with 60 equal to 0. Okay, then we continue here so that we can get 5 VTH minus with 160 equal to 0. Then 5 VTH equal to 160. So that we know that our VTH is equal to 32 volts. All right. So we already have the value for RTH and VTH. So now we can calculate our IN, which is IN is equal to VTH over RTH, where we can get the value. VTH is 32 over 8. So we now know that our IN is actually equal to 4 ampere lah. So now you can draw the equivalent circuit lah. Okay, so the equivalent circuit I just draw here lah. The equivalent circuit you will have here terminal. You have the current which is 4 ampere, and then you have here the resistor which is 8 ohm lah. So this is the equivalent circuit for northern. All right, so this is northern equivalent circuit lah. Okay, if you need to write that back again, but I think in this example they use the source transformation method lah in order to calculate for northern current, where here they transform this part first. Okay, so when you transform that, okay, so this is the Thevenin equivalent circuit. When you transform, okay, you transform, and then this one gonna be this is gonna be, you know that V equal to IR, which is I here 5 times with 5 times with 5, where no, we already transformed from here, sorry, from here, right? So we have V, we want to calculate for I equal to V over R, where we have V 25 over 5, where we will have 5 ampere for source, and then it will parallel with this 5 lah. So that's why you will have this circuit, and then they calculate this value, okay, where we have 20 parallel with 5, where this one is equal to 4, and then when you redraw again the circuit, you will have this lah. Okay, so you will have this will be 5, and then here you will have 3, and then here you will have 4 ohm, and then here you will have 4 ohm lah. Okay, so this is the same directions, right? So you can just add 5 with 3 here. 5 plus with 3, you will have 8 ampere. So you will have 8 ampere, 8 ampere here, and then it will like this lah. You will have 4 here, right? So just draw again your circle lah. 4, and then this is 4 lah. Okay, so you will have this. So this is the circuit that you have when you have the parallel sources and parallel resistor combined lah, just now, which is this one lah, parallel sources with this parallel resistor. Okay, and then after that, from here you can just do the source transformation again, where you want to get the V, right? V equal to IR, where you know that your I is 8 times with 4, where you have 32 volts. All right, so when you have this, then when you draw again, you will have 32 volts, and then series with this 4, and then series with this 4, then you will have this lah. Okay, and then this one part is you need to just add this 4 ampere and then 4 ampere here, so you will get 8 ampere, 8 ohm, 4 ohm plus with ohm because it was series here, so you will have 8 ohm here. So that means that this is your Thevenin resistance, right? So in order to get IN, just do the source transformation once again, where you will have 32 over 8 for ampere for northern theorem, and then you just do the source transformation so that you can have this as your northern equivalent circuit lah. This is just two methods that I show you, where you can just directly calculate using the node voltage as the first example here. Like this example, I'm using the node voltage so that you can just directly calculate for IN, where IN is equal to Thevenin voltage over the resistant voltage lah directly, where the first thing you need to calculate is you need to get these two value lah, VTH and RTH, so then you can get IN lah. And then the other thing that for this example is showing you can use the source transformation lah. Even you can use any other method that you learn in earliest chapters lah. Source transformation, superposition, you can use any other method that you were like to use and comfortable with lah. Okay.
Okay, doctor, I have a question.
Okay.
How we get DTH? Could you please repeat this point?
From this one? From this?
Yeah, yeah.
from here, you can get the VTH by using the node voltage. Because you know the node, the VTH from this two terminal circuit, right? So this one, the VTH is here lah, because this is nothing gonna do because it was open circuit here, right? So you just need to calculate the VTH here, and you know that this is the node for the VTH lah. So just use the node voltage analysis lah. All right. So
Okay,
then
thank you so much.
when you get then you can just do the transformation here like this lah, because you know that like just draw the directions of current is all leaving this node, so I can just add all the equations lah and then equate with 0 lah, because there is no positive current. Okay.
Okay, thank you.
I have a question as well.
Okay. Mm-hmm.
Uh, 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 the voltage theorem, which was the closest line to the open circuit. If we have two nodes, do we also do it like V1, V2 like that, or?
Yeah, you have to calculate both value if you have two node, or else you cannot get the value lah.
Okay, thank you.
All right. It's just you need to solve it using, because I think that I'm showing you the previous example with the Thevenin, right? So you need to calculate all the node that you have in the circuit in order to get the Thevenin voltage lah, because from the circuit it's all related, right? So you need to calculate all the values lah. Okay. So we have another example here for the northern equivalent circuit here. So based on this example, okay, so you just draw IN equal to VTH over RTH, or you can just, you know that IN is also equal to ISC lah. So it's up to you, but I like to use this one. Like first you calculate for the VTH and then you can calculate for the RTH lah, because this RTH is actually equal to Rn. Okay, first one, like we calculate for the Rn here, which is the northern resistance lah. Okay, if from this circuit, you know that we only have the independent source, right? We have only voltage and current source. So means that in order to calculate for the resistance, we can just turn off this part. So when we turn off, then we can just redraw again the circuit where we only have this, right? Okay, so we will have this terminal, we have this 3, we have this 3, and then we have this S6 lah. So from this circuit, both of this one and this one is series, right? Is it? This 3 ohm and 3 ohm here going to be in series. Okay, because sorry, when you turn off this going to be open circuit lah, here going to be short circuit, so there is no connection here. So you will have your Rn, which is 3 plus with 3, and then it's going to be parallel with 6. Okay, so when you calculate, okay, I'm showing you here, when you calculate you will get 3 ohm lah. Okay, 3 plus 3, because this one is turned off. When you turn off this one, it's going to be short circuit, and then when you turn off the current, it will be open circuit lah. So just 3 plus 3, and then parallel with 3, and then parallel with 6, and then when you calculate, you can get it equal to 3 ohm lah. Okay, and then after that, in order to calculate for IN, or you can just calculate for the VTH lah. So if you want to calculate for VTH, the VTH is here lah. All right, or here lah, is the same directions lah. Okay, you can calculate for the no, this is the VTH, and then here you can just put the V1 lah, because this is the difference node lah. Okay, because when you put the node here, you directly calculate the VTH here lah. Okay. So you can calculate that, or you can use any other method like mesh if you want to use the mesh analysis, all right? But for this example, it uses the source transformation here, okay? So from this circuit, you can transform the source in order to find this IN here lah. Okay. All right. So for the IN here, so you just put the short circuit here, short circuit current, right? Because IN is equal to the short circuit current. So just put the short circuit current here, where is in this direction. So you can have that. Okay. So when you have the short current here, so you know that this resistor is not going to be connected because there is no current supply here lah. So you can just ignore this this resistor lah, and then just redraw again your circuit where it's going to be this circuit lah, where you don't have the 6 ohm resistor, because when you put the short circuit current, there is no connection for 6 ohm lah. Okay, because there is no current supply here. So okay, so means that you can using this circuit using the source transformation lah. Okay, so from this part it will transform the current lah. So you know, in order to get the current V over R, so 15 over 3, so that you can get the 5 ampere, and then it's going to be series with these 3. Okay, so from here you know that your current is here, right? So you can combine this current where you have 4 plus with 5 plus with 4, you're gonna have, this is 9 lah, 9 ampere, and then you know that okay, when I draw the circuit again, you will have this is 9 ampere, and then you will have this lah, you will have this circuit, okay, terminal. So this circuit, you know that you can have the current divider lah. You can use the current divider where you have this 3 and this is the 3 ampere. Okay, so you want to get this IN, right? This IN here. Okay, so means that you want to calculate this I lah, ISC here. So what you do is that 3 over 3 plus 3, 6 times with 9. So what you get is this one you're going to get 3, and this is this one you're going to get 1 over 2, and then times with 9. So then you can get the current is 4.5 ampere lah. Okay, so this is your IN, and then you can just draw your equivalent circuit lah, where you have here your IN, which is 4.5 ampere, and then series with your RN here, which is equal to 3 ohm. So this is your northern equivalent circuit lah. Okay, so here is your northern equivalent circuit lah. All right, okay. So if you want to calculate with node voltage, it's going to be the different case lah, because you need to get these two value and then just come up with the equations lah. You need to get the two equation and then calculate for VTH and then V1. So then you can get the value for IN lah, where IN is equal to VTH over RTH. Okay, if you use the node, means that you want to find the VTH first, and then you can use that VTH over RTH to get the northern current lah. Okay, so means that for this one, you need to have these directions of current here. So the first node and the second node where we put it here, VTH lah. So for the first node, what you have is V1 minus 15 over 3. This is the opposite direction, where minus 4 plus with V1 minus VTH over 3 equal to 0. This is the first equation. And the second equation is going to be this one lah, the entering and leaving. So it will be equate together lah, where you will have the second equation, V1 minus VTH over 3 equal to VTH over 6. So this is your second equation. So you need to solve for these two equations, and then you can get the VTH as well the V1 lah. But the one that we want to use the value, which is VTH lah. Okay. find the northern equivalent. So you know that for the northern equivalent, you need to find IN and RN lah. Okay, with respect to the terminal of A and B lah. Alright, okay, for this example, we were using the mesh analysis in order to calculate for ISC here, where this is the short circuit current, where the short circuit current is equal to IN lah for this one. All right. Why is it using the mesh analysis? Because if you analyze the circuit, it's already have the current here, and then it's easy for you in order to get this current here lah, because it's just the short circuit current, right? So means like for this loop here, you will have ISC lah. Okay, like for this one, you will have this one is already 4 ampere for this loop, and then this one going to be I1 and IC. So means like for this one, you need to calculate for I1 and ISC lah. Okay, but you want to get this value lah for this ISC, but you need also to calculate for I1 lah. Okay, all right. So you know that you have these two loops that you need to come up with the equation, because this one is already have the value for the current. Okay, so let's say we want to have the equation for I1 here. So just follow the current directions for the mesh here. So you know that starting from here, it was -60. Okay, and then you can just add these two resistance, the total of the resistance that it have in that loop, which is plus with 50 ohm, 50 I1, 50 I1 here, and then minus with 40 ISC here, 40 ISC, and then 10 times with 40 lah, minus with 10 times with 4, 10 times with 4, okay, and then equal to 0. So then when you do the simplification, you will get -60 plus with 50 I1 minus with 40 ISC minus with 40 equal to 0. And then when you simplify it again, you will have 50 I1 minus with 40 ISC equal to 100 lah. Because when you add up is this one 60, -60, -40, you will have -100, and then you bring it you bring the -100 on the other side, so you will have the 100 lah. So this is going to be your first equations lah. Okay, and then we want to get the equation in ISC. Okay, in ISC here, so just total up the resistance here, where 40 plus with 8, you will have 48 ISC. Okay, and then minus with 40 I1, and then minus with 8 times with 4, where you will have 32 lah, equal to 0. So then you will have 48 ISC minus with 40 I1 equal to 31 lah, when 32 when you bring this 32 here. So you have this equation, two equation lah. So we have this 1 and 2, and then you need to solve both of these, and then when you calculate, you will get ISC is equal to 7 ampere lah. So this is also equal with your northern current lah. Okay, and then you know that in order to calculate for your RN, okay, in order to calculate for your RN, which is equal also with the RTH, so you know that in this circuit there is no dependent source. So you can just directly calculate by turning off these two sources lah. All right. When you turning off these two sources, when you turn this, it will be open circuit, and then when you turn off this voltage, it is going to be the short circuit, right? So if you redraw again the circuit, you will have like this lah. Okay. You will have the circuit like this lah. So you will have here 10. 40 and 8. So in order to find the resistance here, so means that 10 parallel with 40, and then you need to plus with 8. So when you calculate, you get this lah, 16 ohm resistor for the northern resistance lah. Okay, and then this, when you want to just draw again the northern equivalent circuit, so this is the northern equivalent circuit lah. Okay, circuit, you will have this is as IN and this is your RN. Okay. Okay, so we have also the northern versus Thevenin. This is only for your informations lah. Okay, these two equivalent circuit can be related to each other. Of course lah, it's going to be from northern, you can just convert it into Thevenin, or from the Thevenin, you can convert it into northern, because you know that for northern, you will need to have the IN and also the RN, where this RN is also equal to RTH and this IN is equal to ISC. Okay, and then for the Thevenin, you know that you will have the Thevenin voltage and also the Thevenin resistance lah, where this Thevenin resistance is also equal to Rn, and from this Thevenin also you can calculate for the In lah, where In is equal to VTH over RTH, and for this one also is going to be the same lah. If you want to calculate for VTH, it's going to be In times with Rn, so you can get this VTH value lah. So it was like the source transformation source transformation theorem lah, vice versa for the northern and the Thevenin lah. Okay, so that's why it are the northern and Thevenin are related to each other lah. Okay. All right, and then with Thevenin voltage, northern current and the resistance are related. Finding the Thevenin or northern equivalent circuit requires you to find the open circuit voltage, where we know that VOC is equal to VTH lah, all right. And then the short circuit current, where we know that the short circuit current is equal to IN. And then the equivalent or input resistance at terminal A and B when all independent sources, right? So this is for the case for the all independent sources are turned off lah. When you have all the independent sources in your circuit, you know that RTH is equal to Rn, and it also same for if you have the dependent source, but the method to calculate for the RTH is different lah. Okay, you can just you cannot just simply turn off the source and then calculate. You cannot do that lah if you have the dependent sources. All right. Okay.